Hello everyone, I am Darshan A, Assistant Professor of Mathematics. In the previous sessions, you have learned groups, subgroups, normal subgroups, quotient groups and so on. In this session, you are going to learn how to compare any two groups. In particular, you are going to learn how to compare two groups for their structural similarities. Let us consider a group G and a group G dash. Let me denote the elements of group G by these colored circles. Let us denote the elements of group G dash by these colored squares. Suppose in group G, if I combine the yellow circle with the blue circle, I get the red circle. It might happen in group G dash if I combine the yellow square with the blue square in the exact same order, I get the red square. If it happens for every pair of elements in G, then the map which maps the colored circle to their respective colored square is a homomorphism. The word homomorphism is derived from the Greek words homos and morph, which means same shape or same structure. Let me define homomorphism formally. Let G be a group under the binary operation star. Let G dash be a group under the binary operation dot. Then the function f from group G into group G dash is said to be a homomorphism if f of a star b is equal to f of a dot f of b for all a b in G. Suppose if there is no scope for confusion, we just write f of ab is equal to f of a, f of b. In the LHS, ab means a star b. In the RHS, f of a, f of b means f of a dot f of b. This is a visual representation of group homomorphism. Here the group G star is mapped to group G dash dot under a mapping F. The image of the element A under the mapping F is f of A. The image of the element B under the mapping F is f of B. Now the combination of A and B with respect to the binary operation star is A star B. This element maps to f of a dot f of b, which is the combination of f of a and f of b with respect to the binary operation dot. Now let us consider an example. Show that the function f from z plus to z plus defined by f of x equal to 2x is a group homomorphism. Here the binary operation in the domain group is addition and the binary operation in the codomain group is also addition. So we have to show that f of a plus b is equal to f of a plus f of b for all ab in the domain, that is z. Let ab belongs to z. First consider f of a plus b, the LHS, which is equal to 2 into a plus b, which can also be written as 2a plus 2b. Let me take this as equation number 1. Next, consider f of a plus f of b, the RHS. f of a is 2a, f of b is 2b. Let me take this as equation number 2. If you observe equation 1 and equation 2, they are identical. So we have f of a plus b is equal to f of a plus f of b. Since the elements a, b are arbitrary, this relation is true for all a, b belongs to z. Hence, f is a homomorphism from the group z plus into the group 2z plus. Next, we shall consider one more example. Let G be a group if x phi is equal to E for all x belongs to G, where E is the identity element of the group, then show that phi is a homomorphism on the group G. We need to show that AB phi is equal to A phi B phi for all AB in the group G. First, let us take AB in G. By the definition, A phi is equal to E and B phi is also equal to E. By the closure law, we have, since A comma B belongs to G, AB also belongs to G. Hence, AB phi is equal to E. Now I consider A phi into B phi. A phi is equal to E and B phi is equal to E. By the identity law, E dot E is also equal to E. From the equation 1 and equation 2, we have AB phi is equal to A phi B phi for all AB in G. Hence, phi is a homomorphism on G. Now consider the next example. Check whether the function f, which maps x2 to x plus 1, is a group homomorphism or not on the additive group of integers. The function f is defined from z plus to z plus by f of x equal to 2x plus 1. We need to check whether f of a plus b is equal to f of a plus f of b or not. Let us take two arbitrary elements in Z, a, b. First consider f of a plus b. By the definition, we have f of a plus b is equal to 2 into a plus b plus 1, which is equal to 2a plus 2b plus 1. Next, we consider f of a plus f of b. F of a is 2a plus 1 and f of b is 2b plus 1, which is equal to 2a plus 2b plus 2. If you observe equation 1 and equation 2, here we have 1 and here we have 2. So, f of a plus b is not equal to f of a plus f of b for some ab in Z. Hence, f is not a homomorphism on Z plus. Now I consider the next example. Show that the function g, which maps the additive group of real numbers to the multiplicative group of positive real numbers defined by g of x equal to e power x, is a group homomorphism. Here the binary operation on the domain group is addition. The binary operation on the codomain group is multiplication. So we need to show that g of a plus b is equal to g of a into g of b for all ab in R. First, take ab in R. Consider g of a plus b, the LHS. G of a plus b is e to the power of a plus b. Next, consider g of a into g of b. G of a is e to the power of a, g of b is e to the power of b. By the law of indices, we have e power a into e power b is equal to e to the power of a plus b. From equation 1 and equation 2, we have g of a plus b is equal to g of a into g of b for all a b in R. Thus, the function g is a homomorphism from R plus to R plus dot. Now I consider the final example. Let us consider the group G equal to minus 1 comma 1 under usual multiplication. Show that the function f, which maps the additive group of integers z plus to G under usual multiplication, defined by f of x equal to 1 if x is even, f of x equal to minus 1 if x is odd, is a group homomorphism. For a, b in Z, we have 4 different possibilities. Both a and b can be even, or a is even, b is odd. A is odd, b is even. Both a and b can be odd. By the definition of f, if a is even, we should have f of a equal to 1. Since b is even, f of b is also 1. Similarly, for even 1 minus 1, here we have minus 1 and 1, here we have minus 1 and minus 1. Since the binary operation on the group G is usual multiplication, f of a dot f of b becomes 1 into 1, 1, 1 into minus 1, minus 1, minus 1 into 1, minus 1, minus 1 into minus 1 plus 1. If a is even and b is even, a plus b should also be even. If a is even, b is odd, a plus b should be odd. If a is odd, b is even, a plus b should be odd. And if both a and b are odd, then a plus b should be even. Now f of a plus b becomes 1, minus 1, minus 1 and 1. If you compare these two columns, they are identical. So from the above table, we have f of a plus b is equal to f of a into f of b for all a b belongs to Z. And therefore, f is a homomorphism from the group Z plus to the group G dot.